Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, what we're going to do is we're going to have a look at a software tutorial, this time though using Minitab as our software of choice. Hope you enjoy it. Okay, welcome to the latest Minitab tutorial, and today what we're going to take a look at is doing a screening DOE followed by a modeling DOE using Minitab. So I'm going to go to a simulation just to create some data and to show you how to do a DOE screening first, then modeling. So if I go to my simulator, I've got this little scenario here of a riveting process. If I switch the process on, look, you can see the hydraulic hammer starts to work. And we're hitting rivets into a surface. Let me see if I can show you the data of the results a little bit better. What we should be hitting there is 0. That error is how far proud or how far below the surface the rivet is being hit. So the idea is that we hit the rivet flush to the surface. So we want to be as close to 0 as we can possibly be. So if I show you the current performance, let's go to a capability window, generate 100 data points. There's the current performance, look. We're hitting an average of 26.34 millimeters proud. You can see there's far too much variability. We've got to try and make that shape fit inside the tolerances. Plus or minus 10 millimeters is the aim. And so that's the current performance. If we look at the process, how many variables do we have? Hydraulic pressure, rivet density, surface temperature, hammer friction, hammer type, and fluid type. So we actually have 6 variables at 2 levels. So let's take a look at the highs and the lows for those 6 variables, and let's take a look at our DOE strategy. Okay, so here are the 6 variables. So you can see the hydraulic pressure, the high and the low, look, 800 to 850. The rivet density, 100 to 120. Surface temperature, 40 to 50. Hammer friction, 35 to 55. And fluid type and hammer type, well, they're just 2 types of fluid, 2 types of hammer. So you can see the design space that we have to test. So we have essentially 6 variables. We are going to test them at 2 levels. So what's our DOE strategy? Well, because we have 6 variables, we are going to screen first, and then we are going to model. Let's take a look at the DOE menu that I typically use. Here it is. This is the 2-level DOE menu. You can see, look, depending on how many factors you have, 2, 3, 4, 5, or 6 to 11, then this is the menu that I use. Now obviously in Minitab has an extensive menu. We can do many different DOEs, but for practical machine-based DOEs, these are the DOEs that I use. 2-level DOEs, Taguchi L12 for screening, factorial designs for modeling. So because we are down here, we have 6 factors. We have to start with an L12, and then we're going to follow it up probably with an 8-run full factorial. So we're going to do 2 DOEs, one after the other. And that's the DOE strategy that we're going to use on this process. So let's go back to the process and let's do the DOE. Now in this little simulator, I can go to the DOE window. I can ask it to do an L12, look, 2 levels, L12. If I click through this, select all the variables, next, next, and finish and generate some data. Then I get an L12 created for me based on the way that this process works. Now we're going to take that data into Minitab, then we're going to analyze it, and then we're going to do another DOE, take that data into Minitab and analyze it. So this first DOE is the Taguchi L12. So let's go to Minitab. Now to save time, I've already got the DOE and the data into a Minitab worksheet. You can see, just scroll it across, look. You can see the 6 variables, you can see the data. It's all in a table, you'll notice. It's not down in a column like Minitab would normally do this, because this is a Taguchi design. And besides, I like to be able to look across the row here. This is really important to me. I like to be able to see that I've got some consistency across the rows. So I really want the data to be in tables. So here is the L12. It's all set up for me to do some analysis. So here we go. Stat, DOE, Taguchi, analyze Taguchi design. So the first thing it's asking me for is where is the data? So I've got to tell it it's in those 4 columns. Then I get a choice to decide. Now normally it's got the signal to noise and the means switched on here. I've switched those off and I've gone to the graphs, and again signal to noise would have been switched on, but I've switched that off. I just want the mean and the standard deviation main effects plots here, and that's the only analysis I want to do with an L12. It is a graphical screening analysis only. So if I click OK to that, and I click OK to that, what I now get is 2 graphs. So let's pop these out, slide that over there. Get the other one so I can see it first. Here's the second one. Okay, so we have 2 main effects plots. Let's just put them side by side. Now the first plot I'm going to look at is the one on the right, the standard deviation plot, because what's that telling me? Well, it's telling me rivet density is driving the standard deviation. If you remember the performance of this process, it was way too variable to fit inside the tolerances. We need that rivet density to help us. And where are we going to put rivet density? Well, of course, we're going to go to the 100 down here. We're going to go to 100 because we want to minimize standard deviation. So that's the standard deviation graph dealt with. Over here, I just want to identify big signals with which I can bully the process. So I can bully the process with the hydraulic pressure, the fluid type, and the hammer type. And that is the screening DOE completed. So if I go back to the design space, so okay, what have we just decided? Well, what we've just decided is this. The variables that shift the mean, the important ones, hydraulic pressure, fluid type, hammer type, they are going to go into a second experiment, a 2 to the 3 full factorial modeling DOE. For the standard deviation, what did we learn? Well, the standard deviation, we learned that rivet density must be fixed to 100. That's what we learned. Now obviously what this means is we've dealt with 4 of the 6 variables, but now what we need to do is we need to deal with the 2 that we haven't talked about yet, which is these 2. So we need to decide to fix them somewhere. So I'm going to choose to fix surface temperature to 50 and hammer friction to 35. I'm going to fix rivet density to 100, and then we'll do another experiment on the same machine. So you are now walking back up to the machine. Let's go back to my simulator. Here we are, we've gone back to the machine. Now before we do anything else, look, let's dial in our fixed variables. Rivet density to 100. That gets the standard deviation under control. Surface temperature to 50. Hammer friction is already at 35. And now I can do another DOE. So if I go DOE, 3-factor full factorial. Pick the 3 factors. What that will do is it will do the 2 to the 3 full factorial, and it will leave the other 3 variables where I've put them. If I go next, next, finish, fill the table. Now look what I've got is a 2 by 3 full factorial. If we take that and put it into Minitab, then we'll analyze it, we'll get a model, and we'll get a prediction on how to hit the target, which is 0. Let's go to Minitab and analyze this data using the DOE function. Okay, here is that data now in Minitab. And now it's a full factorial, and I can simply analyze it as I've done before. So now I'm going to go stat DOE factorial, analyze factorial design. It's asking me where I'm going to analyze. Now I'm going to analyze this column here. You'll notice again, let me just cancel this out. You'll notice, look, that I've set this pattern up so that it didn't randomize, and therefore I could put my data as a block, and I could see I got consistency across the block. That's very important to me. I want to look across these rows here, and I want to see some consistency in my experiments. I want to know my experiments have been properly controlled. I don't want a randomized pattern. That's not the way I want to view my data. This is completely different to the way science researchers like to do this. This is a machine-based DOE, practical. We want to get this right, and I want to be able to see that there's some consistency. So then when I come to do the analysis, I have to put a summary column in for the Y bar here to be able to hit the target. So if I go stat factorial, analyze factorial design, I'm going to analyze the Y bar column because that contains all the information from the 40 data points that I'd collected. Now if I go terms, I'm going to need to turn the terms down from 3, where it normally is, down to 2. I need to get rid of 1 term in order to create some degrees of freedom to analyze this pattern. And so I've thrown away the 3-way, which is very rare in physics. And I click OK to that. Then let's have a look what graphs it's going to give me. Well, it's going to give me the Pareto, that's fine. Let's have a look at the options here. I'm not going to change that at all. And the results, well, it's going to give me lots and lots of results here. I don't want the analysis of variance. I don't want the model summary. I don't want the regression equation, the aliasing structure. I don't want the fits and the diagnostics. I just want the coefficients. So I just want the model. And if I click OK to that, let's have a look. Now I've just got a nice simple table. I've got my p-values here that tell me whether these terms are important or not. I seem to have, let's have a look, the hammer type potentially could be taken out because of the high p-value here, but because it's involved in, let's have a look, hammer type, hydraulic pressure versus hammer type, I've got a p-value which is 0.5 here. So hammer type's going to have to stay. I'm going to remove the, Let's have a look. I'm going to remove the two-way, the hydraulic pressure fluid type, and I'm going to remove the hammer type fluid type. So let's re-regress and let's take those terms out of the model. So if I go stat, analyze design, let's just move this over here so that I can see what I'm looking at, so I can see my p-values. So terms, which terms do I want to get rid of? I want to get rid of the type fluid type, that's the BC interaction, so that's got to go. And I want to get rid of the AC interaction, and I'm going to leave the BC in. So the AB interaction, and because I'm leaving that, the AB interaction, the rule of hierarchy says leaving hammer type. Click OK, click OK, and now I get my reduced model. P-value here, look, has changed, so the hammer type really should go, so should the two-way interaction. I'm going to take those out. So that can go. Hammer type can also go now. So we just ended up with AC in the model. And there we've got p-values of 0. There's the model right there that we're going to use to optimize. So now I'm going to go to the optimizer and ask it to hit 0, which is the target. So factorial, response optimizer. We're going to optimize to the target. Target is 0. Don't need to do anything else to this. Just going to click OK. What does it tell me? It tells me to go 800 with fluid type 2. 800 with fluid type 2. And it says that if I do that, I will hit 0.77. So not quite 0, but 0.77. So 800 on the hydraulic pressure, 2 on the fluid type, and it's predicting that I'm effectively going to hit 0. Let's see if the prediction works. There we go. We predicted that we'd be positive 0.77 of a millimeter. We're a millimeter out from that, so you can see we're slightly off center. But hey, that's a model. That's a model that's working. It's hit the target. You can also see, just a reminder by the way, I dialed this rivet density down. And look now, because I've dialed the rivet density down, the results fit inside the tolerance. So if I put that back up, just to show you a second, if I put that back up to 120, and then I generate 100, watch how much variability there is now. So look at the mess that that's created. So you can see that not only did I control the mean of the process, I also controlled the standard deviation of the process. So let's just go back to our original design space and review what we've decided. So our best settings. $800, 2 on the fluid type, 100 for the rivet density. This was fixed to 50. This was fixed to 35. And this one has been fixed now also to 2. So the main settings, 800 and 2 for the mean. The standard deviation is controlled by the rivet density. And you'll notice the rivet density information came from the first DOE, hitting the average came from the second DOE. Now that is how to do screening and modeling using Minitab.
Okay, well, I hope you enjoyed that little tutorial on that subject. If you've got any questions about Minitab that you want me to help you with, or indeed any questions about Six Sigma at all, or indeed Lean, please drop me a message either in the comments below. Please subscribe also. But you can also leave me an email. If you send me an email on any question and you need a little bit of advice, I'm more than happy to help you out. And of course, if you want me to come and help you inside your factory fix a technical problem, please drop me a line. I hope to hear from you soon.